Have you ever, clicked a link and just wondered what is actually happening in that split second? Well, it turns out a tiny microscopic messenger is taking an absolutely epic journey across the globe. So let's pull back the curtain on this hidden world and follow the secret life of a single data packet. It really does feel like magic, doesn't it? You click, and boom, the internet delivers. But it's not magic. It's an incredibly fast, super complex, but really elegant process. And today, we're gonna pull that curtain back and make that invisible journey visible. All right, so our story starts the very moment you make a request. You click on something. But before that simple click can go anywhere, it has to be properly prepared for its big journey. This is the moment a data packet is born. Okay, so how do computers all over the world, made by tons of different companies, all agree on how to talk to each other? Well, they follow a universal set of rules. And a great way to think about this is the OSI model. It's basically the official 7-step travel guide for any piece of data. Think of it like a digital assembly line or a post office. As your request moves down these 7 layers, each one adds another wrapper of information. For instance, the network layer, that's step 5, slaps the destination IP address on it, kind of like putting the street address on an envelope. Then, all the way down at the bottom, the physical layer turns the whole thing into the actual electrical signals that travel through the wires. Every single step is crucial to get the packet ready for its trip. So, our packet is all packaged up and addressed. What's its first challenge? It's got to navigate its immediate surroundings, your home, your office network, and find the exit. Inside your local network, the first thing our packet is going to meet is a switch. Now, the switch is basically a local traffic cop. Its whole job is to look at the packet's local address and point it toward the right exit, making sure it doesn't get lost among your laptop, your phone, and your smart TV. Now, to get around, our packet uses 2 different kinds of addresses, and this is super important. The MAC address is your device's permanent, unchangeable hardware fingerprint. It's who the device is. The IP address, though, that's temporary. It's just where it's living on the network right now. The switch uses that permanent MAC address to direct traffic locally, kind of like a mail carrier who knows the names of everyone who lives on their street. So how does the switch know which device is which? It uses something called ARP, or the Address Resolution Protocol. You can just think of it as a local phone book. When the switch needs to send our packet to a certain IP address, ARP just looks it up and finds the matching MAC address, that unique fingerprint, so it knows exactly which physical device to talk to. And this brings us to the final step of leaving home. Once the packet finds its way through that local maze, it arrives at the router. The router is the gateway. This is the device connecting your small local town to the huge global highway of the internet, and it's about to send our little packet on its way. And our packet has left the building. Now we're into Act 2 of its story, a crazy high-speed race across this massive interconnected web of networks that we all call the internet. You know, the internet isn't just one single road. It's this unimaginably complex web with endless possible paths. Routing is simply the process of intelligently picking the best path for our packet to take at any given moment, hopping from one router to the next all over the globe to find the fastest way to its destination. So how on earth does it make those choices? It's all thanks to these powerful routing protocols, with names like OSPF and BGP. The easiest way to think of them is as the internet's GPS. They're constantly talking to each other, sharing updates about traffic jams and network outages, so they can calculate the absolute fastest route for our packet in real time. What if a packet gets lost? What if it gets stuck in some kind of loop, just bouncing between 2 routers forever? That's where something called time to live, or TTL, comes in. It's basically a countdown timer. Every time the packet hops to a new router, the number goes down by 1. If it hits 0, the packet is just deleted. It's a simple but absolutely crucial safety net that stops the internet from getting clogged up with lost data. So after a journey that took just milliseconds, our packet has arrived. It's at the right network, but its job is not done yet. Now it has to find the exact service it's looking for on that server. It's time to knock on the right door. When you send data, you basically have 2 main options. There's TCP, which stands for Transmission Control Protocol. Think of that like sending certified mail. It's all about reliability. It guarantees every single piece arrives and in the right order. Then there's UDP, the User Datagram Protocol. That's more like a postcard. It's super fast, but there's no guarantee it'll get there. For loading a web page, we absolutely need reliability, so our packet is definitely using TCP. To build that reliable connection, TCP does something called a three-way handshake. It's actually pretty polite. First, your computer sends a packet that says SYN, which is like, hello, can we connect? The server replies with SYN ACK, which means, yes, I hear you and I also want to connect. Finally, your computer sends one last ACK to confirm. It's this little digital handshake that makes sure both sides are ready to talk before any real data gets sent.
Okay, so we've got a connection, but a connection to what? The IP address got our packet to the right building, the server, but that server might be running dozens of different services. The port number is like an apartment number. It tells the server exactly which application, in this case the web server, our packet is trying to talk to.
And, for the most common services, there are basically famous, well-known apartment numbers. So our request for a web page is probably headed to port 80 for regular web traffic, or port 443 if it's a secure HTTPS connection. These standards just make sure our packet finds the right service every single time. Success. Our request was received and understood. The server now has the web page data we asked for. But hold on, the story isn't over. All of that data now has to make the same crazy journey, but in reverse, all the way back to your screen. So now this server becomes the sender. It chops the web page up into a whole new series of packets, addresses every single one to your IP address, and sends them on their way. And yeah, each of these packets is going to use those same GPS-like protocols, BGP and OSPF, to find the best way back to you. Now, on the way back, these packets are probably going to run into a firewall. A firewall is just like a security guard for the network. It inspects all the incoming traffic and checks it against a list of rules. And since your computer started this whole conversation, the firewall sees these return packets, recognizes them as expected traffic, and says, yep, you're good to go, letting them right through. By the way, if you happen to be using a VPN, this whole journey, both ways, happens inside a secure encrypted tunnel. A VPN basically wraps your data packets in this extra layer of privacy, which makes it almost impossible for anyone on the public internet to spy on what you're doing. It's like sending your mail through a private armored courier instead of just the regular public post office.
And finally, the packets arrive back at your computer. They travel up through those 7 OSI layers, but this time in reverse, getting unwrapped at each step. Your browser grabs all the reassembled data, renders the code and the images, and the web page appears. The packet's quest is finally complete. From your single click through layers of protocols, across local switches and global routers, all the way to a server and all the way back. This entire insane journey happens hundreds, maybe thousands of times per second, usually in less than a tenth of a second. It really makes you wonder, what other incredible invisible systems are working all around us, powering our modern world?